1. First observation of CP violation in baryons at CERN, unlocking matter-antimatter mysteries. 2. Universe's antimatter mystery explained. How matter beat antimatter after the Big Bang. 3. CERN's new discovery. Why our universe has more matter than antimatter. 1. First observation of CP violation in baryons at CERN, unlocking matter-antimatter mysteries. Imagine a universe where matter and antimatter exist in perfect harmony, only to be torn apart by a fundamental force that favors one over the other. This is the intriguing reality that physicists have been trying to unravel for decades, and a recent breakthrough at CERN's LHCb collaboration has brought us one step closer to understanding this phenomenon. For the first time, experimental evidence of charge parity, CP symmetry violation in baryons has been observed, and the implications are profound. But here's where it gets fascinating. This discovery could hold the key to explaining why our universe is dominated by matter, with barely a hint of antimatter in sight. The standard model of particle physics, our current understanding of the universe's fundamental forces, predicts that CP symmetry should be violated in certain interactions, but the extent of this violation has been a topic of intense debate. The LHCb collaboration's findings, which are consistent with the standard model, have sparked a flurry of excitement among physicists, and for good reason. The discovery of CP violation in baryons, the building blocks of matter, could provide a crucial constraint on theoretical attempts to extend the standard model and explain the matter-antimatter asymmetry in the universe. To understand the significance of this discovery, let's take a step back and explore the concept of CP symmetry. In the early universe, the Big Bang produced a vast amount of matter and antimatter, which eventually annihilated each other, leaving behind a tiny excess of matter. This excess, which makes up the universe as we know it today, is not explained by the standard model, and its existence has puzzled physicists for decades. In the 1960s, physicists James Cronin and Valentine Fitch conducted an experiment that showed the weak interaction violating CP symmetry, indicating that matter and antimatter could behave differently. This groundbreaking discovery led to a deeper understanding of the universe's fundamental forces and earned Cronin and Fitch the Nobel Prize in Physics in 1980. Since then, numerous observations of CP violation have been made in other mesonic systems, and the phenomenon is now an accepted part of the standard model. However, the CP violation produced through the Kabibo-Kobayashi-Moskawa (CKM) mechanism, which describes the probabilities of quarks changing into each other, is much smaller than what would be required to create the matter excess in the universe. And this is the part that most people miss. The CKM mechanism, while successful in explaining CP violation in mesons, falls short in explaining the matter-antimatter asymmetry. The LHCb collaboration's discovery of CP violation in baryons, which are composed of 3 quarks, has significant implications for our understanding of the universe. The team, led by Xiueding Yang of Peking University, analyzed the decays of beauty baryons and antibaryons, which are heavy cousins of neutrons, and found that the CP violation observed was consistent with the standard model. But here's the controversy. While the discovery is a major breakthrough, it also highlights the limitations of our current understanding. The CP violation observed in baryons is still much smaller than what would be required to explain the matter excess in the universe, leaving physicists to wonder if there are other mechanisms at play. As Tom Browder of the University of Hawaii notes, theorists will try to interpret this within the context of the standard model, and there have already been some attempts, but there are some uncertainties due to the strong interaction that preclude making a precise test. The research, published in a paper in Nature, has sparked a lively debate among physicists, with some arguing that the discovery could provide a constraint on extensions of the standard model, such as CP-violating decays involving dark matter. So what's next? As the LHC enters its 3rd run, physicists hope to acquire more information on the intermediate particles involved in the decay, which could provide further insights into the nature of CP violation. The question on everyone's mind is, will this discovery lead to a deeper understanding of the universe's fundamental forces, or will it reveal new and exciting possibilities that challenge our current understanding? We invite you to join the conversation and share your thoughts. Do you think the discovery of CP violation in baryons is a major breakthrough? Or is it just the tip of the iceberg? What implications do you think this discovery could have for our understanding of the universe, And what further research do you think is needed to fully understand the nature of CP violation? 2. Universe's antimatter mystery explained. How matter beat antimatter after the Big Bang. Imagine a universe where everything you know, stars, planets, even yourself, shouldn't exist. That's the puzzle physicists are trying to solve as they delve into one of the most profound mysteries of cosmology. Why is our universe overwhelmingly made of matter, while antimatter seems almost absent? This imbalance, which defies expectations set by the Big Bang, has baffled scientists for decades. But here's where it gets fascinating. Recent findings from an international team of researchers might have uncovered a crucial clue that could rewrite our understanding of this cosmic conundrum. Let's start with the basics. The Big Bang, the explosive event thought to have birthed the universe 13.8 billion years ago, should have created equal amounts of matter and antimatter. In theory, these two forms of existence are like mirror images of each other, with antimatter being identical to matter except for having the opposite electric charge. If the universe were perfectly symmetrical, matter and antimatter would have annihilated each other upon contact, leaving behind only energy. Yet we live in a universe teeming with galaxies, stars, and life, all composed of matter. So what tipped the scales? The answer may lie in something called CP violation, a phenomenon where the laws of physics treat matter and antimatter slightly differently. CP stands for charge conjugation, swapping particles with their antiparticles, and parity, flipping spatial directions, akin to looking in a mirror. If the universe treated matter and antimatter identically, CP symmetry would hold true. However, experiments over the years have demonstrated that this symmetry can be broken, a process known as CP violation. CP violation isn't just a quirky detail. It's a cornerstone of our quest to understand why matter dominates. Without it, the universe would likely be an empty void. While evidence of CP violation had previously been observed in mesons, particles made of quark-antiquark pairs, its presence in baryons, three-quark particles like protons and neutrons, had remained elusive until now. On July 16, scientists working at the European Organization for Nuclear Research, CERN, announced a groundbreaking discovery. For the first time, they observed CP violation in the decay of a specific type of baryon called the λb0 baryon. This heavy subatomic particle consists of three quarks, an up quark, a down quark, and a bottom quark, and its antiparticle counterpart, the λb0 bar, contains the corresponding antiquarks. By studying how these particles decay into simpler components, researchers uncovered a subtle but significant difference in behavior between matter and antimatter. In their experiment conducted using the Large Hadron Collider LHC, scientists analyzed billions of proton-proton collisions to spot rare instances where λb0 baryons and their antiparticles decayed into specific combinations of particles. Specifically, they examined decays resulting in a proton, a negatively charged kaon, and two pions, one positive, one negative. They then compared the frequency of these decays for both the λb0 baryon and its antiparticle. Here's why this comparison matters. If the fundamental forces governing the universe treated matter and antimatter equally, the decay rates for the particle and its antiparticle would match. Any deviation would signal CP violation. To ensure accuracy, the researchers meticulously accounted for potential biases, such as slight imbalances in how often λb0 baryons versus λb0 bar antibaryons were produced or detected. They achieved this by analyzing a control channel, a similar decay process not expected to exhibit CP violation, to isolate the genuine effect. The result? A striking asymmetry emerged. The CP asymmetry, the relative difference in decay rates, was measured at approximately 2.45%, with minimal uncertainty. Statistically speaking, this finding deviates from 0 by 5.2 standard deviations, surpassing the stringent 5 sigma threshold required to claim a discovery in particle physics. According to Dr. Meenakshi Nayak, an experimental high-energy physicist from the Indian Institute of Science, Bengaluru, this historic breakthrough deepens our understanding of the matter-antimatter asymmetry and opens new avenues for exploration. While this discovery marks a monumental step forward, the magnitude of CP violation observed so far doesn't fully explain the vast disparity between matter and antimatter in the universe. Scientists believe there must be additional sources of CP violation, yet to be discovered. These could involve unknown particles or forces lurking beyond the standard model of particle physics, the theoretical framework describing the building blocks of the universe. What makes this research particularly intriguing is its broader implications. It addresses a question so fundamental that it borders on philosophical. Why does anything exist at all? Every atom in your body, every celestial object in the night sky, owes its existence to the fact that matter somehow gained the upper hand over antimatter shortly after the Big Bang. By unraveling the subtle ways nature favors matter, scientists are piecing together the story of how our universe evolved into the vibrant tapestry we see today. But here's the part most people miss. This isn't just about solving a scientific riddle. It's about challenging our assumptions about reality itself. Could there be alternative explanations for the dominance of matter? Are we missing entire dimensions or exotic particles that influence CP violation? And this is where opinions diverge. What do you think lies beyond the current understanding of physics? Share your thoughts in the comments below. And let's spark a conversation about the origins of our universe. 3. CERN's new discovery. Why our universe has more matter than antimatter. Imagine a universe where everything we know and see could simply vanish in an instant. It's a terrifying thought. Yet this is the fundamental question that has puzzled scientists for decades. Why did our universe not annihilate itself moments after the Big Bang? A groundbreaking discovery at CERN, the European Organization for Nuclear Research, located on the French-Swiss border, brings us closer to understanding this cosmic mystery. Everyday life as we know it is made up of matter, the stuff that forms our bodies, the Earth, and the stars. But there's a shadowy counterpart to matter called antimatter, which exists in much smaller amounts. Matter and antimatter are like mirror images of each other. They have the same mass but opposite electric charges. For instance, a matter proton has an antimatter antiproton partner, and a matter electron has an antimatter positron partner. But here's where it gets controversial. The behavior of matter and antimatter isn't perfectly symmetrical. This week, researchers at CERN's LHCb experiment published a paper in Nature revealing a significant discovery. Matter particles called baryons decay at a different rate compared to their antimatter counterparts. Decay, in particle physics, is the process where unstable subatomic particles transform into lighter, more stable particles. Cosmological models suggest that equal amounts of matter and antimatter were created during the Big Bang. When matter and antimatter meet, they annihilate each other, leaving only pure energy. It's a wonder, then, that we don't live in a universe made only of leftover energy. However, observations show that antimatter is incredibly scarce compared to matter. This means that matter and antimatter must behave differently in some way, leading to the disappearance of antimatter and the persistence of matter. But how does this happen? While the standard model of quantum physics identifies some differences between matter and antimatter, these differences are too small to explain the vast amounts of antimatter that have seemingly vanished. This leads us to a tantalizing possibility. There must be additional fundamental particles or effects beyond the standard model that could account for these differences. The LHCb experiment's precise measurements of the differences between matter and antimatter could be the key to unlocking these new particles and the physics that led to our universe as we know it. Previously, differences between matter and antimatter were observed in mesons, particles made of a quark and an antiquark. Now the LHCb team has discovered differences in baryons and antibaryons, which are made of 3 quarks and 3 antiquarks, respectively. Crucially, baryons make up most of the known matter in our universe. This is the first time we've seen such differences in this group of particles. The LHCb experiment, operated by an international collaboration of over 1,800 scientists from 24 countries, achieved this groundbreaking result by studying over 80,000 baryons and their antimatter counterparts. The team found that these baryons decay into specific subatomic particles slightly more often, about 5% more frequently, than their antimatter counterparts. While small, this difference is statistically significant and marks the first observation of such behavior differences in baryon and antibaryon decays. While this new measurement is consistent with the small level of differences predicted by the standard model, it's a significant step forward. We're now seeing differences in the behavior of matter and antimatter in the particles that make up most of the known matter in our universe. This could be a crucial step toward understanding why our universe is made of matter and not antimatter. As the LHCb experiment continues to gather data, we hope to uncover any signs of new fundamental particles that could be present. The implications of this research could be profound, potentially reshaping our understanding of the universe's origins and its future. So, what do you think? Could this discovery be the key to unlocking the mysteries of the cosmos? Or do you think there's another explanation for the dominance of matter in our universe? Share your thoughts and join the conversation in the comments. And this is the part most people miss. The discovery at CERN isn't just about understanding the past, it's about shaping our future. As we delve deeper into the mysteries of matter and antimatter, we're not just uncovering the secrets of the universe. We're paving the way for groundbreaking technologies and a deeper understanding of our place in the cosmos. So, what do you think? Is this discovery the key to understanding why our universe is made of matter? Or is there another explanation? Let's discuss.